Welcome to part 3 of the presentation on performing broadband 220 GHz VNA calibration and measurement techniques. The presentation focuses on the VectorStar ME7838G system. So for this final part, we'll start off by first describing some of the important instrument attributes that contribute directly to the accuracy and stability of a broadband system. So beyond things like raw directivity that we described in the first part, we'll now start to show some of the examples of actual instrument performance. And then that instrument performance will lead us into discussing the calibration accuracy and repeatability that we can achieve in a broadband system such as the ME7838G operating up to 220 GHz, and then provide comparison and example measurements of this system using the 220 GHz MPI probes. So there are some additional broadband VNA instrument attributes that would be of interest in many applications. For instance, things like trace noise. This would affect basic data integrity, usually on a finer scale. Drift. This has been discussed in relationship to raw directivity of the system. So drift is important in that it determines the calibration interval, which can be quite important. Good power control allows setting the millimeter wave module power output to a low enough level in order to measure devices well within the linear region. This can often be quite low and well below the minus 30 dBm range. Good power control is also useful when measuring components into the nonlinear regions by sweeping the power of the VNA output. Low noise floor is important not just for dynamic range, but also for signal to noise interests when the DUT drive level needs to be at very low levels. As mentioned, good power control is an important enabler to ensure the power applied to the device is operating well within the linear range of the device, and for situations where we want to drive that device into compression. Since many on-wafer devices such as transistors and LNAs start to compress as low as minus 50 dBm, it is important to have a range of power control that can set the VNA source power to the desired level. As shown previously in the NLTL module diagram, each source band provides an electronic ALC control loop for a wide range of power level control. The ALC circuit provides fast leveling based on a real-time heterodyne ALC loop and power stabilizes in generally under a microsecond. So this plot shows level control down to minus 55 dBm and up to minus 12 dBm at 220 GHz. And as far as noise floor levels, here we see a noise floor at the higher frequencies that continues to be in the minus 100 dBm range. Since the architecture focuses on optimized raw directivity, the end result is a system with good stability over a 24-hour period, even when in a lab environment with plus or minus 3 degrees Celsius. So the plot on the left shows stability in the plus or minus 0.1 dB range up to 220 GHz. And the plot on the right displays the reflection stability over that same 24-hour period. If we want to evaluate the calibration of a 220 GHz system, one thing we might do is measure a delay line usually found on the calibration substrate. This can provide insight into the integrity of the calibration since the device is reasonably known. Another check in the calibration evaluation is to measure the same device with another well-known system. For example, a 110 GHz system could be calibrated using a different set of calibration standards. Then, that system can be used to measure the same delay line, and the measurements can be checked for agreement. So this is a plot of a 220 GHz and 110 GHz system measuring the same delay line, and there is general agreement in the two plots to the limit of the 110 GHz system. Notice that there is also a rise in the plots in the 150 GHz region. So since the two calibrations and measurements were performed on a metal chuck, and it was described previously about the potential for parasitic modes, it might be informative to perform these calibrations and measurements on a ceramic chuck. So here we have the two systems measuring a delay line, but this time both the calibration and measurements were performed on a ceramic chuck. Both systems track each other as before, but now we no longer have the rise in the measurements in the 150 GHz region, and the behavior is more like what we would expect. Another popular technique for checking calibration performance is to compare measurements of other known devices, such as Beatty standards and waveguide attenuators at higher frequencies. The 145 GHz VectorStar VNA offers a coaxial verification kit that also contains a 0.8 mm Beatty standard. The Beatty standard is a stepped impedance beaded airline. Since this device can be accurately machined, it is useful as a known mismatched device that is stable. So it would be useful to measure the 0.8 mm Beatty standard with three different systems, the 125 GHz, the 145 GHz, and 220 GHz broadband systems up to the 145 GHz range and compare the results. You can see in the plot that the three systems correlate quite well, thus adding a level of confidence in the calibrations. So for frequencies above 145 GHz, it would be useful to measure a WR5 waveguide attenuator. Since the attenuator can be used down to 110 GHz, the 125 GHz VNA can measure that attenuator up to the limit of the system. Another VNA configuration that can then be used for comparison using a baseband VNA operating a WR5 band waveguide millimeter wave module. So the second plot demonstrates again good correlation between the three VNA systems across their operational range of frequencies. Besides calibration and measurement correlation across VNA systems, calibration repeatability is an important figure of merit of an integrated measurement test. So this graph shows typical repeatability of the multi-line TRL calibration calculated from two calibration series that were performed within about 30 minutes and by an average skilled operator. The multi-line TRL repeatability is compared against the sum of the system drift, contact repeatability, and LRM calibration repeatability. The related RFTAG 95th conference paper describes how we calculated the characteristics. The increase in the air-bound spread above 200 GHz is primarily due to the degrading signal-to-noise ratio. We perform these calibrations and measurements at a relatively low output power, minus 30 dBm at the flange reference, that corresponds to about minus 35 dBm at the probe tip at 220 GHz. Such power level might be needed for the characterization of advanced active devices. That is why this measurement was intended to explore the boundaries of possible device characterizations. Here we have the transmission coefficient of a symmetrical 3 dB verification attenuator measured with 3 probe touchdowns, A, B, and C. The average attenuation was as expected, and consistency of the data is impressive. As you can see, it is hard to distinguish the 3 measurement series from each other. So we looked at the vector difference between traces, normalizing the last 2 of them, the traces B and C, to the first series, A. And so these are the vector differences for S11, those are marked as match, and S21, marked as trans. We observed the maximal vector difference for traces B and C versus the first trace A is at minus 30 dB for both transmission and reflection parameters. The deep match conditions, the trace match where we measure very small quantities, represent the worst case. So, in conclusion, we have considered the system architectures, measurements, and calibration characteristics of an on-wafer broadband 70 kHz to 220 GHz single-sweep VNA system. We discussed the critical and challenging parameters of the system and shown that a 220 GHz on-wafer measurement system addresses the needs of the millimeter wave and device characterization industries. Thank you very much for your attention. I hope this series was helpful in understanding how the VectorStar ME7838G broadband system combined with the MPI 220 GHz Titan probes can be used to sweep from 70 kHz up to 220 GHz for on-wafer device characterization and other on-wafer measurements.